Hello friends, welcome to the channel Physics by IITians. We are back with another important series and this today we shall discuss about the question from classical mechanics. We will briefly explain the physics and understanding the questions. So let's start the video. The first question is a rigid body is constrained to move on a plane. Number of degrees of freedom for it will be. So you have a rigid body and that rigid body is constrained to move on a plane. So there will be total 3 degrees of freedom because 2 for the translation and 1 for the rotation. Suppose you have a plane here on the screen and you fix one rigid body. Okay, not fixed. In that plane there is a rigid body. Suppose there is a ball. So the ball can move along x direction, the ball can move along y direction, and the ball can also rotate. Okay, so the rotation is the xy plane, within the xy plane. So the rotation is 1 degrees of freedom and the translational degrees of freedom is 2. So total it will have 3 degrees of freedom. Now the formula for the to find out the degrees of freedom is F equals to 3n minus k, where n is the number of particles subjected to k independent constraints. Now we shall understand what is the meaning of degrees of freedom. The degrees of freedom is the number of independent ways in which a mechanical system can move without violating any constraint which may be imposed. And this is called the degrees of freedom, or the number of different coordinates, independent coordinates that can describe its motion. This is called degrees of freedom. So we should know some more examples to find out the degrees of freedom. Suppose you have a free particle, okay, and you are taking three-dimensional Euclidean space. That is, you have 3 coordinates x, y, z, and the particle is also free. So how many degrees of freedom it can have? It can have 3 degrees of freedom because it can move along x, it can move along y, it can move along z. So now for one particle it is 3. If there are n number of free particles, then, or if there are 3 number of free particles, then each of the particle have 3 degrees of freedom. So that will be 3 into 3, that is 9. Or for n number of free particles, degrees of freedom will be 3n. Now suppose this n number of free particles are not free right now. You are imposing or they are experiencing some constraint. Constraint means that is something, the restriction on their motion, and these are the number are called the constraint. We will also look on the constraint in some other question. So for k number of constraint or k number of constraint relations, if there are n particles, the degrees of freedom will be 3n minus k coordinates. Suppose we take an example of a fixed fulcrum of a simple pendulum. Fulcrum means the support where the pendulum is hanging. So it is fixed. So suppose the point of fix on ceiling, the degrees of freedom will be 3 into number of particles minus number of constraints. Now here number of particles is 1 because fulcrum is the point or some small particle. So it is 1. So 3 into 1. Now number of constraint is also 3 because it cannot move along x, it cannot move along y, it cannot move along z. So 3 minus 3 will become 0. So it is fixed. It has 0 degrees of freedom. Do you understand what I trying to say? The degrees of freedom means the motions, how in which coordinates their motions are possible, or they are independently they can move or rotate or they can do some motion. Now we take another example, the bob of a conical pendulum. What is conical pendulum? Conical pendulum actually nothing but like a simple pendulum. The difference is simple pendulum will do to and fro motion like this way, but conical pendulum do this rotational motion. And if you take the projection of this conical pendulum motion, you will get, this is, suppose this is the rotation. So you will get the exactly simple harmonic motion. If you do the projection, suppose at some point, this is the mass of the pendulum, or this is the most point where the pendulum is at certain instant of time. If you take the projection, then you can get the linear harmonic motion or simple harmonic motion. So this is the basic difference between a conical pendulum and a simple pendulum. We want to find out the number of degrees of freedom for the conical pendulum, and it will be, so there will be a fixed there will be a fixed axis for their motion. So there will be some constant. So this constant relation is x square plus y square plus z square equals to L square, where L is the length of that pendulum. So degrees of freedom will be 3 into 1 minus 1, that is 2. Suppose you are taking a dumbbell. Dumbbell means you are taking two balls, suppose two masses, two rigid bodies, and you are fixing them with a rod. This is kind of a dumbbell. So how many degrees of freedom a dumbbell have? A dumbbell can has 3 into 2, 2 for the two particles, minus 1. 1 is for their, this is the constant that along this axis they cannot move. Okay, so this is will impose a restriction on that, on their motion. So 3 into 2 minus 1, so they will have 5 degrees of freedom. Suppose we are taking 3-point masses and they are connected with 3 rigid massless rods. So the degrees of freedom will be 3 into 3 minus 3, because 3 the total number of the particles and 3 are the number of constants. So it will become 6. Suppose you are taking a rigid body, and a rigid body, there is no, it is not restricted. So the number of degrees of freedom is 6, 3 for rotation, 3 for translation. Also, suppose you are now, if the rigid body is not free, it is fixed and fixed at one point. So since it is fixed at one point, we can lose 3 freedom. Excuse me. So rigid body fixed at one point, since it is fixed at one point, we lose 3 freedom. Okay. So hence the number of degrees of freedom, I think something is here that is disturbing. Wait, let me fix it. Okay. So the rigid body fixed at one point, since it is fixed at one point, we lose 3 freedom. Hence the number of degrees of freedom of the system is 6 minus 3. Earlier when it was free, it was 6. Now it is 3. Now this rigid body rotating about a fixed axis. So now it is rotating about a fixed axis in space. So the number of degrees of freedom will be reduced and it will become 1. Certainly, you understand some examples, the idea of degrees of freedom. Now come to the next question. The number of generalized coordinates required to describe the motion of a cylinder rolling without slipping on an inclined plane. So we should know about the physics of the rolling motion of the rolling without slipping cylinder, and then we will find out the number of generalized coordinates required to describe its motion. So for any wheel that is rolling without slipping, we have to consider this constraint, that is S equals to R theta. Because the distance moved by the center of the wheel, suppose it is S, is same as the distance moved by a point on the rim of the wheel. And this S equals to R theta is maintained the constant relation. And the velocity will be ds dt, that is R omega. And the rotation, there will be two types of motion. One will be rotation around the center of mass and the translation of the center of mass. So the kinetic energy have two parts, one with the rotation part, another with the translation part. So here, if you look here, we don't need so much things to describe the general coordinate. We have to know that S equals to R theta. So all we have to understand there, if we find out the R, and if we find out the theta of the particle at certain instant of time, we can describe its motions. So we need only 2 coordinates, or these are called the generalized coordinates, to describe the motion of the solid cylinder. Now we understand how to choose a general coordinate system, because one of our friend has asked me how to choose the generalized coordinate. So how to choose, there follows 3 principles. First, the values determine the configuration of the system. Okay. The next one is they may be varied arbitrarily and independently of each other without violating the constraint of the system. And third one, there is no uniqueness in the choice of generalized coordinates, then our choice should fall on a set of coordinates that will give us a reasonable mathematical simplification of the problem. So we choose our coordinate system according to the behavior of or motion of the system that we need a simplification so that we can get the simple results or easy result. Let us take some examples to understand it deeply. Suppose we are taking a simple pendulum. So here we choose generalized coordinates as theta, where theta is the angle which the pendulum makes with the vertical line through the point of suspension. Suppose we are taking a flywheel. Then again the same, that is theta will be the angle, a definite radiation of the flywheel and a fixed line perpendicular to the axis. A particle moving on the surface of a sphere. We take generalized coordinates as theta and phi because we take the usual polar angles of a point on the sphere. A particle moving inside surface of a cone. So r and theta are the radius vector drawn from the vertex as origin to the position of the particle, and theta is the angle which the radius vector makes with a fixed slant edge of the cone. Certainly, we can understand how to choose our degrees of freedom and how to understand how to decide the generalized coordinates. Now come to the next question, that is the constant of a rigid body is there are given four options: conservative and scleronomic, conservative and rheonomic, holonomic and rheonomic, and non-holonomic and scleronomic. We should understand what is constant. Constants are the restrictions of their motion, and these constants are of different types. How many types there? There are different types of constant. We should know one by one, like scleronomic, rheonomic, holonomic, non-holonomic, bilateral, unilateral. So if when it is scleronomic, if the constant relation do not explicitly depend on time, that is the restriction of their motion, it is independent of the time. Suppose in case of rigid body, there these constants are called scleronomic constants. When it will be rheonomic, when the constant depend explicitly on the time. Suppose this is sliding on a moving wire. Okay. Now suppose a holonomic. When the constant will be holonomic, that is constant relations are can be made independent of the velocity. Then it is holonomic. If the constant relation are not holonomic, then they are reducible function of the irreducible function of the velocities, then it will be non-holonomic. So please try to understand this constant. You can read this from any textbook and you will understand it. The number of constants, and depending upon their nature, whether they are dependent on time or not, whether they are dependent on velocity or not, we will classify them. So our question is, for the rigid body, what will be the constant? Yes, we have also read this, that the constant is scleronomic. The next question is, a particle of unit mass moves in a potential Vx equals to x cube minus 3x plus 2. The question is the angular frequency of the small oscillation about the minimum of the potential. Now, we have to understand it very thoroughly because there are some very specific points about the small oscillation. I will tell you more. First, we should understand how to solve the question. You are given a potential and you are asked to find out the angular frequency of small oscillation about the minimum of the potential. It can be asked to find out the oscillation about the maximum of the potential also. We will understand it thoroughly. So first, the potential has been given as x cube minus 3x plus 2. So to find out the maxima or minima, first we have to find out the point for the maxima or minima. For that, we need to find out the first order derivative, that is del v del x. It becomes 3x square minus 3. I'll make the first order derivative to 0 to find out the points of maxima and minima. So 3x square minus 3 is equals to 0. X becomes plus or minus 1. So to get the minimum potential, d2v dx2, that is the second order derivative of the potential, should be greater than 0. And to get the maximum of the potential, del 2v del x2, that is the second order differential of the potential, should be less than 0. So here at point x equals to 1, this del 2 v del x2 equals to 6, and that is greater than 0. So it is the minimum of the potential, and k is the force constant. And here you have to find out the frequency. So omega naught, and omega naught is related to k as omega naught equals to root over k by m equals to root over 6 by 1, because m has been given as 1 and k is 6 at this point, and minimum point equals to root 6. So here you have to understand why we take k as del 2v del x2, or how does it come from. This is a very interesting thing, and you should all know the physics here. Suppose we are taking a particle that is slightly displaced from the point of its stable equilibrium, okay? And it is slightly displaced, so it will execute simple oscillation because it will try to come to the equilibrium position due to its mass or inertia. It will go some away, then it will try to come back, then go away, then come back. So it will do a simple oscillation or executing small oscillations. What will be the potential energy? The potential energy function can be expressed in the form of Taylor series expansion. So suppose the particle is at point x and the equilibrium position or the minimum position at point x0. So V of x can be expanded in a Taylor series like Vx equals to the potential at a function x can be written as V of x, that is equals to V of x0, that is potential at a function x naught, plus x minus x naught dv dx at x naught, plus half x minus x naught whole square d2v dx2 at x naught, and so on. Now at the minimum, for the minima of the potential or the maximum of the potential, dv dx at x naught will be 0. So surely we don't, the term will be 0. And these terms are negligible if the oscillation are very small, because it will be x minus x naught whole cube d cube v by dx cube. So these terms are negligible. So we can write the potential, that is v of x at any point x equals to v of x naught plus half of x minus x naught whole square d2v dx2 at x equals to x naught. Now, so at the stable equilibrium, this is 0. Now since we can approximate that this is the minimum potential, and we can label this as potential v of x naught equals to 0. So what will be the potential function at the point x? V of x will become half into d2v dx2 at x equals to x naught into x minus x naught whole square. Or we can write it as half k x minus x naught whole square, because it is doing a simple harmonic oscillation where k can be written as d2v dx2 at x equals to x naught. So this is the mathematics behind assuming this form of potential, or we can find out this formula k as d2v dx2 at x equals to x naught, because we are doing Taylor expansion of the potential v of x at the point x equals to x naught. So we have to put dv dx equals to 0 first to find out any points of stable or unstable equilibrium. What we have to find first? We have to find out dv dx equals to 0, then find the values of x, then put this value of x one by one in d2v dx2. If we see d2v dx2 is positive, then that is stable equilibrium point. If d2v dx2 is negative, then that will be unstable equilibrium point. Look here, this is the point of stable equilibrium here, because it will try to come back. Whether it is going away, it will again try to come back. Whether it is going this way, it will again try to come back. And this is the point of unstable equilibrium, because it is somehow, if you just disturb it or perturb the system very slightly, it won't come back to this point. It will go away, whether this side or this side. And at this point of stable equilibrium, d2v dx2 is positive, and at this point of unstable equilibrium, d2v dx2 is negative. Okay. Now the next question is, a solid homogeneous cylinder of radius r rolls without slipping on the inside of a stationary large cylinder of radius r. The period of small oscillation about the stable equilibrium position. So you have a solid cylinder and it is moving, or it is rotating, it is rolling within a big cylinder. Okay, so you have to find out the period of small oscillation. The important here, the point is the small oscillation, because these are all true. The assumptions will be true only if we consider the small oscillations. So let us find out. So look here, this is the diagram. So this is the larger cylinder and this is the smaller cylinder. It is rolling within the cylinder, and this is theta angle and this is the phi angle. We first have to find out the constant of the motion, that is the restriction of the motion. So let phi be the angle which the radius of the larger cylinder makes with the point of contact with the vertical, and theta is the angle that a fixed radius of small cylinder makes with the vertical. So phi is for the larger cylinder and theta is for the smaller cylinder. Now the distance, that is OO prime, equals to R minus R. Look here, this is R, that is the radius of the big cylinder or larger cylinder, and small r is the radius of the smaller cylinder. And this R minus R is O prime point. Okay. So since the cylinder rolls without slipping, the equation of constant is R theta equals to R minus R phi, or capital R minus small r phi, or we can write as R theta dot equals to capital R minus small r phi dot. Kinetic energy T will be the kinetic energy of the translation of the center of mass and kinetic energy of the rotation about the center of mass. So for the translation it will become half m r minus capital R minus small r phi dot whole square plus for rotation half I naught theta dot square. So it will become, after simplifying, you put the value of I naught as half m r square and we get the kinetic energy T will be 3 by 4 m capital R minus smaller r square, smaller whole square phi dot square. The potential energy is minus mgh, where minus mg to h will be minus r minus small r into cos phi. So Lagrangian will be T minus V, that is you put the value of kinetic energy which we get earlier and put the value of potential energy, and then you find out the equation of motion with the help of Lagrange's equation of motion, that is ddt of del L del phi dot minus del L del phi equals to 0, or you can write it 3 by 2 r minus small r whole square phi double dot plus g into capital R minus small r sin theta equals to 0. Now the point small oscillation was important because at a small oscillation phi is very small and sin theta can be assumed as theta, or sin theta can be approximated as sin phi can be approximated as phi. So equation of motion become 3 by 2 r capital R minus small r phi double dot plus g phi equals to 0. Or we can write that phi double dot plus omega square phi equals to 0, where omega equals to root over g by 3 by 2 capital R minus small r. You just compare, you just write this term, you take this 3 by 2 term here, 3 by 2 into whole term, and you write this as omega square, and you leaving this phi dot alone, phi double dot alone. So we get omega as root over 2g divided by 3 into capital R minus small r. So the period of small oscillation T equals to 2 pi by omega, that is 2 pi into root over 3 into capital R minus small r divided by 2g. If you and this is another question that I want that you should practice. The similar kind of question, you find out the constant of the motion first, then find out the Lagrangian, and then find out the period of oscillation. And the system is for compound pendulum. So the period of oscillation for compound pendulum, these are A, B, C, D are the given options. Please solve it and comment the answer. Okay friends, if you like this video, don't forget to like it, don't forget to share with your friends, don't forget to subscribe our channel, and you can help us by clicking the link given in the description box. Thank you.